Thank you for taking the time to join us today. I'm Renping Wang, and I'm the software developer engineer on Amazon Sumerian team. Today, what we are going to be talking about is simulating real-world physics in 3D environment using Amazon Sumerian. So what's on the plan? First, we're going to talk about what's Amazon Sumerian and how people use Sumerian to innovate 3D content. That basically covers how we get here today. Then we're going to spend some time understanding what simulating real-world physics is. With that in mind, we will go through how physics system works in Sumerian. And to better understand some of the features and tools Sumerian have, we're going to go through a demo scene, which consists several physics components and techniques one could potentially use when creating his or her own scene. Eventually, we will cover what we are currently working on and what one can expect from us. Sumerian is a web-based real-time development and publishing platform. You can create, publish 3D immersive AR/VR experiences. It's a fully featured web-based editing environment. You can create visual scripting behavior using state machines. You can bring in your own custom content. We also support many industry standard 3D, 2D, and sound format to bring your content to build the type of experience you want to. We also have a lot of pre-packaged assets to use as well. As you can see here, with pre-configured scene templates and asset packs, along with a bunch of state machine actions and scripting APIs, one can create a 3D scene in minutes. Sumerian also integrates with other AWS services like AWS IoT, AWS Lambda by having a built-in AWS SDK to access a full suite of AWS APIs. Besides, one can also leverage the voice and chatbot features with Amazon Polly and Amazon Lex to make a speaking host easily from scratch as well. As a publishing platform, when you are finally ready to publish your experience, it's publishing to a URL where desktop, handheld devices, and AR/VR headsets can load essentially via a web browser with no install. This is pretty significant value for customer as installation is typically a painful process. In addition, we have demos and tutorials online showing different use cases in different scenarios. For example, product configurators can help customers feel more confident about their purchasing decisions, or creating training simulations to onboard new employees to quickly get up to speed. And please keep in mind, all the content covered so far about Sumerian can also be found at the link you see there below if you'd like to know more about it. All right. So without further ado here, let's jump to what problem we're actually trying to solve today: how to simulate physics in virtual world. Before going into more detail, we need to understand why physics is important in 3D development. First of all, nowadays, simulation in any sense is a common use case in 3D AR and VR application. For example, there will be training simulations for new workers in different industries, robotic simulation for modeling or machine learning purposes, etc. Physics is a rule or baseline to follow to make this simulation to be more realistic and useful. To explain what I mean, for example, when people are in a VR training simulation, they expect to grab or throw things the same way they do in real world. Expect objects to fall due to gravity or move under certain forces like in real world as well. This is normal because of human nature and possibly other movies or games they have experienced before. And apparently, physics is the base rule for all these effects to rely on, since a really good graphics itself wouldn't make a user feel like they're actually immersed if he or she moves unnaturally, passes through walls or floors, or things don't fall or topple as if they had realistic mass and material properties. Another great aspect of using physics is to provide an alternative solution to object movement or animations. Traditionally, manual work is generally required when creating animations for objects. One probably need to make them from scratch, frame by frame. However, physics provides an alternative way and also a realistic way for a bunch of objects to interact with each other in real-world manner. Now, let's think about what makes this a problem or what makes this complicated. First of all, physics simulation itself is a hard problem. It could potentially involve a lot of different aspects such as rigid body dynamics, soft body dynamics, fluid simulation, and so on. Many different algorithms and techniques are required to resolve these problems. For example, in a typical rigid body collision process, there are usually two phases, a broad phase and a narrow phase. Completely different techniques are required for each phase, since broad phase algorithm is usually dealing with a massive number of objects, while may not need precise result between each individual pair. While the narrow phase algorithm is usually dealing with a specific pair of objects, but somehow need more collision info between them. In addition, sometimes one also has to make trade-off between a more precise result and the overall performance, especially when it comes to real-time simulation, which is essentially what Sumerian is targeting for. This leads us to the idea of physics engine, especially 3D physics engine here. In this case, a physics engine is a library for representing three-dimensional world made of discrete objects, which can in turn be composed of multiple shapes. User usually will be able to create and destroy such objects and track their explicit or proximity-based interactions. Object will typically move under laws of classical mechanics, but can also be moved manually by user as well. There are different physics engine libraries existing in the market, and each of them usually has different implementation feature sets, ways to expose itself for usage. However, usually used to achieve the same goal of simulating real-world physics behavior. We will cover what Sumerian uses and how it works with Sumerian in detail later. Besides, it's not enough to just have the physics engine there. Integration is also an important process. At the minimum, one needs to take the state of any moved visible objects in physics engine and update them in the respective rendering representation. And of course, there's a lot more info could be synced other than this, such as notification of any physics event, passing any user request back to the physics engine, and so on. When it comes to Sumerian, it's also important to make sure this update process doesn't break any other systems, which could potentially make changes to these affected objects at the same time. As a result, we have physics system, which is pretty much like many other systems already existing in Sumerian today, such as transform system, animation system. It handles all the communications between Sumerian world and physics world, including copying over transform properly, processing any query requests, and reporting any collision event. It's also acting as an abstraction layer between a physics engine and Sumerian. It's worth noting that physics system has similar implementation to other Sumerian systems, such as having processing priorities, making it not breaking other systems' update process happen at the same time. With all those being said, let's talk about what physics engine Sumerian used before and how it performed. Sumerian used to utilize Canon.js as its underlying physics engine and had a dedicated physics system to accompany its behavior. Canon.js is a pure JavaScript engine inspired by web application use case, and it includes simple collision detection, various body shapes, contacts, frictions, and constraints. However, it turns out that as a lightweight web-based physics engine, Canon has gaps in terms of functionality and reliability. For example, somehow it doesn't support certain types of collision shapes, such as convex hull, capsule, and it doesn't support collision between certain types of shapes either. Besides, sometimes the same object setup can lead to different results, making it a non-consistent simulation. When it reaches a certain number of objects in a scene, there's also a chance that performance can quickly become the bottleneck as well. As is shown here, we ran into some limitation that a specific type of collider may not interact with another. In this case, they are box and tree mesh shaped colliders. On the left, we can see the actual behavior, while we are expecting the result showing on the right. Since we have heard many problems from users of running into show-stopping bug during the early development related to physics, and considering Canon being a no longer maintained engine for a long time, we have decided to move to a new physics engine and completely refactor our physics system as well. After collecting enough data such as ripple health, supported feature set, performance to fill out our comparison matrix, we have decided to use PhysX as our underlying physics engine. PhysX is an open source library with a rich set of features and one of the mostly used physics engines in the industry over the past several years. It's designed to be robust, high performance, scalable, and portable. It has a well-maintained repo since it came out and has previous usage on web platform as well. All of these benefits makes it suitable foundation for Sumerian to start with. To have a quick glance of how PhysX is getting picked. For example, performance is an important factor when using a physics engine. To measure that, we usually perform some kind of stress test. In this case, it's basically a Sumerian scene built using a large number of physics objects with different physics engine or implementations to compare with, and on different devices or platforms Sumerian support. For the quick clip showing here, we run a scene with a bunch of cubes stacking together with PhysX implementation on desktop platform, and then we monitor all the performance data logged out during the scene play. It's also important to factor out any other potential impact to the performance. For example, we use instance rendering technique, meaning all the cubes sharing the same material so that we can eliminate the render impact to the overall performance. And as we can see here, the output is really great in terms of the total number of objects simulated. Okay, so with PhysX being our long-term choice underlying physics engine, now Sumerian is able to deliver more stable, consistent physics behavior to users, along with a rich set of physics features, including not only the rigid body dynamics, statics, recast, but also multiple different types of joints, constraints, and character controls, etc. Besides, scenes targeting for different platforms or hardwares can also benefit from the performance boost as well, making sure them running smoothly even with a large number of physics objects on a low-end device. In addition, PhysX is a trusted engine in industry and has been used widely for many years, meaning that many common quirks and usage scenarios can be found online, along with some high-quality documentations and a thriving community to find assist with. As it is likely the physics engine will be capable beyond the interfaces provided in the Sumerian system, it's always great to have a whole community out there for help when someone trying to create some high-quality experiences beyond the normal use case. Let's introduce some fundamentals of physics properties first, and we will see how they map to Sumerian components and systems later in the demo. In PhysX, a rigid body simulation world is composed with multiple dynamic bodies and static bodies. Dynamic bodies are used to define moving objects with different physics properties such as velocities, forces, and so on, while static bodies are used to define solid objects which are fixed in the world. Each body, no matter whether it's dynamic or static, will contain one or more shapes in general to describe its spatial extent and collision properties. There are different kinds of shapes available to use, including primitive shapes, such as box, sphere, plane, capsule, etc. Physics engine will simply construct these shapes based on the parameters passing in, like half extent, radius, normal vector, and so on. There are also mesh shapes, including convex mesh and tree mesh. They both take the actual mesh data, including, for example, vertices and indices info passing in. However, convex mesh will typically involve a transformation process to generate a new convex hull, while tree mesh is a collision triangle mesh, consists of a collection of vertices and triangle indices, just like the original triangle mesh. And please note, there are some limitations for a body shape combination. For example, tree mesh can only be used within a static body or kinematic dynamic body, so as plane and height field. So be careful when you try to use them the way you want. Now let's open up a demo scene to go over some basic physics features and tools in Sumerian. And feel free to ask questions. We will answer them at our best at the end. Okay, so with the scene open, when we select a Sumerian entity in the entity panel, in this case we select the slope, we can see there are multiple components attached to this entity, including this collider component on the right. So a collider component serves two roles in terms of mapping physics properties to Sumerian. The first one is that it specifies a shape. And from a drop-down list here, we can select from box, cylinder, infinite plane, and sphere. The trigger checkbox will specify whether the shape will be part of the simulation process or only be used to identify if there's overlap for the shape, meaning objects can go through the shape without blocking. And of course, there are more physics material properties such as friction and restitution and shape parameters. In this case, with a box shape, we have half extents for x, y, and z axes. Another role for this collider component is creating a rigid static body in physics world when we play the scene. So the actual physics simulation will begin when we hit play button in editor mode. Here, all the physics body construction and initialization will happen at the same time, since this Sumerian entity only contains one physics component, which is collider component. We will use the shape specified here to create a rigid static body when the physics simulation begins, meaning the slope will be there to block other physics objects. In contrast, if we select this box entity, in this case, collider will be used only to specify the shape, while rigid body component will be used to create a rigid dynamic body in the physics world. It will be a moving body which it will have mass, velocities, and will receive gravity forces coming from other bodies. So we are expecting this box to fall and land onto the slope when we play the scene. Okay, so it's working as expected. Now we can play with the setting a little bit. For example, if we select slope back again and check the trigger checkbox, in this case, we're expecting the box going through the slope instead of landing on it. Let's see how it works. Okay, so here we can see the box actually sit underneath the slope, which is expected. And another interesting aspect is to working with collision event. So let's select the box back again, and from our behavior setting, we drag this state machine behaviors onto this box. We can open up the editor panel of this state machine behavior to see. So in the initial state, it has a listener for the begin contact event, which will emit when the box receives any physics hit event. So after receiving this event, it will transit to the second state, which actually is very simple. It only changes the color of this box. So we're expecting once the box hits the slope, the color should be changed to red as specified in the state machine behavior. Let's go back and play the scene. Okay, as we can see here, it's working as expected. With this example, we pretty much covers all the basic functionalities Sumerian has with physics. We can move on to a little bit more interesting one. Here we have two symmetric setups, each with a ball, a slide, and a turret at the bottom. We have mesh collider attached through scripts to both sides, since it's not available yet through UI, as we can see here. We have tree mesh shape on the right and convex mesh shape on the left. So with these two balls falling, we're expecting the left one rolling over on the torus, while the right one falling through the hole in the middle of the torus. We're also introducing the kinematic checkbox here in the rigid body component of this ball, as we can see here. As we just mentioned, rigid body component will create a dynamic body in physics world, and the kinematic dynamic body means the body will not move due to physics system, but instead fully controlled by the user. We'll see a more typical usage in the next example, but for now, we only use this flag to make sure it doesn't drop until we want it to do so. We have state machine here attached to these balls so that it unchecks the kinematic checkbox when it receives a click. In this case, we can click on these two balls one by one from right to left to compare the actual behavior. Let's play the scene. So by clicking on the ball on the right, we can see the ball falling through the hole in the middle of torus, while clicking on the left ball, we can see the ball roll over from the torus instead of falling through it, which is pretty much the same as we expect. Now we can move to the next example. Here we have a torus hanging over with a cylinder under it, and several boxes set up around them. Two boxes on the right are standard dynamic objects with both rigid body and collider component attached to them, as we can see here. And the box on the left has only collider component attached to it, making it a static body. And we have a torus on the top, which is a kinematic dynamic body here, as we can see. And this torus will move under our control script back and forth, as we can see here. For example, inside the ball joint script, we can specify which other entity we want to tie together with the torus. In this case, it's the cylinder underneath. And within the torus and the other entity, we can specify which local frame we want to use to create the joint between them. In this case, we specify somewhere in the middle between those two objects. So the cylinder under it is just a normal dynamic object with rigid body and collider component attached. When we hit the play button, we can see the torus moving left and right under our control based on the kinematic behavior, and the cylinder is not falling down. Instead, it ties together with torus as it's moving. The static box on the left was not affected, while those two dynamic boxes on the right were hit by the cylinder, so they fall down. This pretty much explains the basic usage of joint constraints. At last, we have this chain example on the left. It consists of 6 cylinders. Each of them is a dynamic object and tied together with the one above it through a ball joint as well. The very top one is a kinematic dynamic object, making the whole system not falling down altogether. We have a state machine behavior attached to the very bottom cylinder, which we can see here. We have a state machine behavior attached to the very bottom cylinder, which we will apply a velocity to it once receive the mouse click. Let's see how it behaves. As we can see here, the velocity of the bottom cylinder is transferred up till the very top cylinder, making the whole chain swing by itself, which is a pretty cool effect with the joint itself there. Okay, so let's jump back to the slide. I'd like to mention about how we get PhysX built and integrate into Sumerian as well. Since PhysX is an open source C++ library, to be able to use it on web platform, the library has to be built into WebAssembly and make Sumerian engine consume the build artifacts. We use EM scripting to build C++ libraries to WASM and JavaScript module. Along the process, as certain C++ feature or syntax didn't work with this compilation, we end up either converting them to proper format or types, or just removing them for now, such as CMD concept, meaning single instruction, multiple data. Besides, we also use embind to expose C++ functions to JavaScript contexts, which not only just requires a separate binding file, but also sometimes needs rewriting the function itself. For example, if a function tries to use a huge mesh data sitting in JavaScript context, there's going to be a special way to directly copy that piece of memory over instead of passing mesh data manually. Okay, to wrap up, today we have a quick overview about pretty much everything related to physics in Sumerian, like what components are there, how they work, and how to use them. And hopefully this set up a basis for everyone who wants to try the physics feature when working with Sumerian. And as for next step, we are currently working on exposing more features in PhysX, such as more collision shapes, different types of joints, etc. as well as making any existing feature more useful, including system refactoring and UX improvements. And last, here's a link to our community site, docs.sumerian.amazon.aws.com. It's really the best resource for information on Amazon Sumerian for anyone who wants to know more about whether it's Sumerian in general or about PhysX specifically. Just navigate to our community site where you can find tutorials, articles, and demos for you to start with. Thank you very much for attending today's webinar. I'm Renping Wang, and I hope everyone enjoyed this webinar and enjoy using Sumerian in the future.